All right, so today we are going to take a look at our notes on freefall. So this is still one-dimensional motion, very similar to what we've been doing before. So there's a couple of things for us to consider. Anything will accelerate due to gravity as long as it's here on planet Earth. However, there's a couple phrases that we're going to be using and a couple things that we're going to be seeing that are very specific when it comes to objects in freefall. So whenever something is dropped, that means that we're holding it still before release, so its initial velocity is going to be 0. Now, if we think about it, any object that is falling through the air that you're holding initially, you let it go and it's going to begin falling towards the ground. Therefore, there has to be an acceleration. It started at rest, and then it gained some velocity a moment later. It's an acceleration, and that's what gravity is. Gravity is an acceleration that affects objects and makes them accelerate towards the surface of the Earth. Galileo Galilei came up with the law of falling bodies. Through a variety of experiments, he concluded, in the absence of air resistance, which is something that we assume on all problems, all objects accelerate towards the Earth with the same constant acceleration. This acceleration is 9.81 meters per second squared. Now, the direction of this can be positive or negative depending on the problem. And what I mean by this is we can decide if it's easier for the problem that downwards towards the surface of the Earth is the positive direction. We can also decide that downwards towards the surface of the Earth is the negative direction, depending on what makes the problem easier. The only thing is, we must maintain that direction at all times. If we say in the beginning that down is positive, then throughout the entire problem, down must remain positive. And this acceleration of 9.81 meters per second squared is only true on planet Earth. Every other body in the universe has a different acceleration. Since gravity is an acceleration, we can substitute it into our three kinematic equations as the acceleration of the object. And since we are now moving vertically as compared to horizontally, we can note the displacement as y instead of x. Vi and Vf are going to pretty much stay the same. So for instance, acceleration times time is equal to the difference in velocity. Gravity times time is equal to the difference in the velocity, and so on, as you can see in the equations. So if we say the object is dropped, the initial velocity is 0, and we can remove that from the equations, thus simplifying our work quite a bit. Now, if an object is thrown, either thrown upwards or thrown downwards, the initial velocity is not 0. Here's where direction becomes very important. We want to choose whichever direction may come out as making the most sense for the motion. So for instance, if we throw an object upwards, it may still be easier to say downwards is the positive direction because the object is going to rise and then eventually fall. This is very situationally dependent. I unfortunately cannot give you a hard and fast answer as to when is the best time to make down positive or to make down negative. It really depends on the question, and you must be consistent. An important thing to remember is that the top of an object's arc, when it's thrown up into the air, when it's at the maximum height, its velocity always drops to 0. That's the point where it goes from moving upwards to moving downwards, going from positive to negative or negative to positive, depending on our directional scheme. When the object returns to the same height it was thrown from, its velocity will always be the same magnitude, aka the value, but it will have an opposite direction. So if we threw it upwards with 10 meters per second of velocity, it's going to be coming downwards at 10 meters per second of velocity. It is important to note, however, that the height may come out as negative if up is positive, down is negative, and the object fell from the starting point. Now, on an inclined plane, gravity still accepts the object, or still accelerates the object, I should say. Gravity's going to pull it straight down, but the incline is in the way. Now, we know that if you place an object on an incline, it's going to accelerate downhill, but with not quite the same acceleration. So in this case, we have to use what's known as a component of the acceleration. And I'll spare you the derivation of how this comes out, but we multiply the acceleration of gravity by the sine of the incline of the hill. That will tell us how much of the gravitational acceleration is actually affecting the object. Then that value can be plugged into the kinematic equations just like any other acceleration. And then we will take a look at these examples in class.